Introduction to metamorphic rocks. Metamorphic rocks are rocks that have changed from their original form due to changes in temperature, pressure, or chemical composition. They are different from sedimentary rocks, which are formed by the accumulation of sediments, and igneous rocks, which are formed by the cooling of magma or lava. Metamorphic rocks can form in different ways. Some metamorphic rocks are formed when existing rocks are buried deep in the Earth's crust and exposed to high heat and pressure. This process is called regional metamorphism. Other metamorphic rocks are formed when existing rocks come into contact with hot fluids or magma. This process is called contact metamorphism. Metamorphism versus diagenesis. Metamorphism. It is a process that changes the mineralogy, texture, and composition of rocks due to high temperature and pressure conditions, usually associated with deep burial or tectonic activity. Metamorphism can produce new minerals, foliation, recrystallization, and deformation in rocks. Examples of metamorphic rocks are gneiss, schist, marble, and quartzite. Diagenesis. It is a process that alters the physical, chemical, and biological properties of rocks due to low temperature and pressure conditions, usually associated with sedimentation and burial. Diagenesis can produce compaction, cementation, dissolution, replacement, and bioturbation in rocks. Examples of diagenetic products are clay minerals, calcite, quartz, and fossils. Metamorphic rocks, formation, classification, texture, and structure. Any rock derived from pre-existing rocks by mineralogical, chemical, structural, or textural changes in solid state, in response to marked changes in temperature, pressure, and chemical environment at depth in Earth's crust, i.e. below the zone of weathering and cementation, is called sedimentary rock. The rocks derived from igneous rocks are called orthometamorphic rocks. Example: gneiss. The rocks derived from sedimentary rocks are called parametamorphic rocks, e.g. slate. Agents of metamorphism. Metamorphism is the process of formation of metamorphic rocks from sedimentary and igneous rocks. During this process, different agents are involved. These agents are called agents of metamorphism or metamorphic agents. The following are the different agents of metamorphism. Heat. It is the most important metamorphic agent because it provides the energy to drive chemical reactions that result in the recrystallization of existing materials and/or the formation of new materials. Here's how heat causes metamorphism. Thermal energy results in recrystallization and dehydration. Thermal energy breaks chemical bonds. They increase the rate of reaction. Heat leads to changes in mineralogical composition and crystals, and that leads to coarse texture. Earth's internal heat comes mainly from radioactive decay within the Earth's interior and converging plates. Pressure. There are two types of pressure acting during the formation of metamorphic rocks: uniform pressure and directed pressure. They are also known as equidimensional pressure and directed pressure. Uniform pressure leads to a change in the volume of rock by pore space reduction due to closer atomic packing, while directed pressure leads to changes in shape, texture, and structure. Chemically active fluids. The change in rocks due to chemically active fluids takes place through a partial or complete solution of the minerals. The most chemically reactive fluids derived from magma and other sources are water, carbon dioxide, etc. They lead to chemical changes in rock.
Types of metamorphism. Metamorphism is broadly classified into three major categories based on the dominant agents involved in the formation of rocks. 1. Contact metamorphism, thermal metamorphism. It results from the emplacement of a hot igneous intrusion into cooler country rocks at relatively low pressure. Here are some of the features of contact metamorphism. Heat is the dominating factor. The metamorphism operation area around the magma intrusion is called contact aureole. Changes in mineral composition and texture. Commonly formed carbonate-rich country rocks. Contact metamorphic rocks are usually massive. For example, limestone to marble. 2. Regional metamorphism. It occurs over wide areas, hundreds of kilometers, and within large organic, mountain building process, belts. Temperature and directed pressure are dominating factors. Regional metamorphism is also classified into the following two types. Regional dynamothermal metamorphism. It results from the thermal gradients in a broad region. The rocks are characterized by the parallelism of platy and elongated minerals. It changes both mineral composition and texture. Regional beryl metamorphism, high-grade diagenesis, It results from the thick piles of hydrous sediments or fragmental volcanic materials due to several hundred degrees of temperature with high water pressure. This is due to a lack of significant parallelism of metamorphic mineral grain. It is difficult to identify but only possible in a polarizing microscope. For example, zeolite, glaukophane, etc. are beryl metamorphic minerals. 3. Dynamic metamorphism, cataclysmic metamorphism. Here are the features of dynamic metamorphism. Occurs in zones of intense deformation as fractures, faults, etc. at shallow depths. Change in texture such that decrease in grain size. Mechanical deformation produces rocks ranging from bridges to milenites. Texture of metamorphic rocks. The texture is used to describe the size, shape, and arrangement of grains within a rock. Foliated texture. Most igneous and sedimentary rocks consist of mineral grains that have a random orientation. By contrast, deformed metamorphic rocks that contain platy minerals, micas, and/or elongated minerals, amphiboles, typically display some kind of preferred orientation in which the mineral grains exhibit a parallel or specific alignment. This preferred orientation of a rock's minerals is called a foliated texture. Gneissic texture. During high-grade metamorphism, ion migrations can result in the segregation of minerals. Although foliated, gneisses will not usually split as easily as slates and schists. Gneisses that do cleave tend to break parallel to their foliation and expose micro-ridge surfaces that resemble schist. Non-foliated texture. Not all metamorphic rocks exhibit a foliated texture. Those that do not are referred to as non-foliated. Non-foliated textures usually form in environments where parent rocks are composed of minerals that exhibit equidimensional crystals, such as quartz or calcite. Another texture common to metamorphic rocks consists of particularly large grains, called porphyroblasts, that are surrounded by a fine-grained matrix of other minerals. Porphyroblastic textures develop in a wide range of environments and result in very large specimens of certain minerals, such as garnets. Structure of metamorphic rocks.
The large-scale feature developed in metamorphism is metamorphic structure. They have been measured in hand specimens. 1. Cataclysmic structure. It is the metamorphic structure formed under directed pressure such that stress resulting from deformation like folding. 2. Maculose structure. It results from thermal metamorphism in argillaceous rocks, dark-colored minerals giving a spotted appearance, e.g., slate. 3. Schistose structure. It is formed under stress by platy or flaky minerals in parallel orientation. In micas and equidimensional minerals, for example, biotite schist. 4. Granulose structure. It results from heat and uniform pressure in equidimensional minerals by the process of recrystallization. It is also known as a saccharoid structure. For example, quartzite, marbles. 5. Gneiss structure. It is a banded structure due to the alternation of dark-colored and light-colored minerals by the highest grade of metamorphism through regional metamorphism, for example, gneiss.